Hello, everybody, and welcome to the Decouple Podcast, where we explore the science and technologies that can decouple human well-being from its ecological impacts, and the politics that can make decoupling possible. Welcome back to the podcast. Today I'm joined by Mark P. Mills, who is a senior fellow at the Manhattan Institute and a faculty fellow at Northwestern University's McCormick School of Engineering and Applied Science, where he co-directs an institute on manufacturing science and innovation. Early in his career, Mark was an experimental physicist, and he holds a degree in physics from Queen's University in my home province of Ontario here in Canada. Mark, welcome to the podcast.
Thanks for having me. I'm virtually back in my homeland.
There you go. There you go. So, Mark, I should have forewarned you, but I do like to get my guests to kind of introduce themselves after I get their bona fides and accolades out of the way. But, pretend you're at a dinner party and you got sort of 60 seconds to kind of chat someone up. Maybe talk about how you became interested in the things that you're interested in now.
I try not to do that at dinner parties. I've been warned away from that by my wife and many other people. It's staying away. Well, I spent my early career in doing what I have often called real work, building, inventing things that have patents. I worked in microprocessors and missile guidance, fiber optics. I was involved in the nuclear industry. And if you, being a Canadian, may remember, Canada undertook a major parliamentary directed investigation into whether or not the country, Canada, should continue the pursuit of commercial nuclear energy. This was on the heels of the debates, not because of accident issues. These are the debates over proliferation and non-proliferation, right, whether that was controllable. And there was the Porter Commission hearings headed up by Sir Arthur Porter in Toronto, which was an adjudicated proceedings, which I attended. Fascinating. Canada, the Commonwealth does things like that. We're a little different than blue ribbon panels in America because it was adjudicated. You're sworn in. It was like being in a trial.
Right.
So my interest in understanding how things work comes out of what I did when I was working as a scientist and as an engineer. I've worked at Bell Labs Canada, Bell Northern Research, as well as the RCA, David Sarnoff Research Labs, United States. I like how things work, understanding how they work, both the science and the engineering. And in energy, I got, by accident, I sort of fell into the nuclear field because physicists know something about nuclear physics, not all. And that journey, if to use that overused word, took me into the public debate over nuclear energy when it was hot on non-proliferation. And it was something I was very interested in. I worked on it, in fact, in the Reagan White House Science Office on the non-proliferation issues. And that also took me, as it happens, to end up being at the site of the accident at 3 Mile Island during the accident.
Interesting.
And then I spent the next 5 or 6 years doing what I would call apologizing for nuclear energy. It was on TV, radio, debating all the anti-nuke kooks. And I used the word kook deliberately. There were a lot of kooky things said about nuclear energy back in the 70s and early 80s. And so I found myself immersed in this debate over energy, about the ethics of energy, what engineers could or couldn't do, what constituted risks that we could know and couldn't know, the moral, ethical, economic cases. It's all the debates we're having now, all of them, without exception, are the same as the debates we had decades ago about nuclear energy. The difference is that time we were told, and people can use a magic Google machine to know that I'm not using hyperbole here. We were told that the very end of the planet was at threat because of nuclear energy, that we had to stop nuclear power plants from being built because humanity's mere existence was at risk. And that we had to split wood, not atoms, for example.
Right.
In one of the earliest calculations that I remember doing about this idiotic trope, but it was a very catchy phrase, was I said, well, I've cut down trees. I used to cut down trees in the forest in Canada with my neighbor, real dangerous occupation, as you know. Yep. But he had a dual fuel oil wood furnace, and that's back when oil was expensive, as you know. And because I liked the fun of it, stupidly, I didn't want him to hurt himself. I would go and cut down trees with him and
Yeah.
cut them up. So I calculated whether or not Canada, never mind the rest of the world, could operate its energy ecosystem and its electricity on splitting wood instead of atoms. And you can imagine this is a knowable calculation. We know how fast trees grow in a northern temperate climate, and maybe you want it to be sustainable, so the damn trees have to be let grow enough to be harvestable. And I'm ignoring here the issues about hardwoods that last hundreds of years. We're just assuming the environmentalists then didn't care about preserving 10-century-old trees. They just wanted to replace oil, gas, coal, and nuclear power. I mean, unsurprisingly, the calculation yielded idiotic results. You'd just be harvesting most of the land area that was arable in Canada to sustain its energy appetites by replacing coal and nuclear power. So that's a long answer to my roots in this debate began in Canada over the nuclear debates. Now here we are, full circle. Some people in the nuclear community, rather the environmental community, like nuclear energy again. Like you probably talked to Schellenberger, my buddy. I call him my buddy. I mean, I know Michael, smart guy. He's right about most things, certainly about the need for nuclear energy. But we're back full circle with a huge swath of the environmental community still in firm opposition to nukes. Many of them are the same people. I mean, all of us are still alive from those debates. So we're debating the same issues with the same clouds, making the same silly statements that they made then all over again. But people have forgotten how silly they were.
Although I guess that the sort of Rube Goldberg machine has changed a little bit from something as simple as this idea of splitting wood, not atoms, to these
now we're just going to spin windmills instead of splitting atoms.
Right. And interconnect them all and deal with these challenges. And that's what I want to get in this conversation and what I want to explore with you, because you're someone who I think can really help us. The way I'm thinking about this is sort of getting under the hood, right? My son is obsessed with cars right now. He's only 2, but I always try and lift up the hood and show him what's under there and how it might work, break that down for him. And I think, I think about city kids who just get their food at the grocery store and they've never been out to the farm. And when they do, it's a total shocker to them. And maybe they become vegetarians as a result or something like that. But
I lived in farm country. Yeah, I know what you mean.
But as a result of growing up in the sort of comfortable Western lives that we do, because of urbanization, because of our use of really dense energy sources, we don't get to look under the hood. We don't see what's happening, and we take for granted a lot of the comforts that we have, and we don't understand some of the underlying implications of the choices that we make. So, with your engineering expertise and your study and understanding of innovation and manufacturing, I was really excited to sort of have you come on the show and be a bit of a tour guide and explore some of what you've called this magical thinking, these kind of Rube Goldberg machines. So I wanted to start off because, I think a large part of the origins of this magical thinking have to do with this, I think what you've called like the misapplication of Moore's law to energy. And, these ideas that we can get, just exponentially better at producing energy with exponentially fewer inputs. You talk about, because I think you're a physicist, you talk about things like the actual physical limitations of the number of, photons hitting the Earth that we can turn into electrons. Can you walk us through some of those concepts, like the Betz or the Shockley Kaiser, or even the Carnot as well? I mean, just how the real world physics, limits us in a way that it doesn't with computing. How are the two things different?
Well, I mean, you put your finger on the thing that I guess I would say animated me or annoyed me most about the tropes. So let me start with a predicate about my particular biases or views, broadly speaking. There's always new physics. So we deal with the physics we understand today, but new physics doesn't come along very often. And going from new physics to new technologies takes a very long time. Nuclear energy was new physics in 1939. We still have a de minimis amount of energy produced from splitting atoms. It's very hard to do, it turns out. We're getting much better at it. So, and I also am a firm believer in the power of innovation, that people can do things that are sort of unimaginable. I mean, engineers, I discovered, having worked as one, I wasn't trained as one, are great at the workaround. Right? Yeah. You tell an engineer you can't do this. Oh, okay. What about if I do it this way? It looks like I tricked Mother Nature, right? So the workaround is so magical that you sort of think there's always a workaround. Right? So just give them enough money, and that can work around the limits. But what I tried to do is look at that, realizing that there are always workarounds, but there are always boundaries. There's limits to what is doable. So let me use a simplistic way of categorizing and give you maybe some physics specific answers, but you cited Bett's law and the Shockley limits and those kinds of things that I have in my papers. But if I say that when airplanes were first invented, I mean, people wanted to fly for a long time, and the way, everybody knows humans tried to do it wasn't very, flapping your arms with wings on it didn't work so well. You can almost do that now with wingsuits, but you're not flapping your arms. You're really just falling, and it's a controlled fall, not flying.
Yeah.
But the airplane is a workaround, obviously. And once the propeller-driven airplane was invented, it got faster and faster and faster from 50 to 100 mile an hour airplanes, and it kept getting faster. But we know two things about propeller-driven airplanes. They can't break the speed of sound because they use air. They're pulling air by them, and you can't go faster than the air can move.
Right.
So there's a physics limit to how fast a propeller-driven airplane can go. So you have to invent a new machine that's a jet, which pushes and doesn't count on pulling air. And neither of them can fly to the moon because there's no air. They're airplanes. So I can say it with a certainty, airplanes can't go to the moon. There's no workaround. You have to invent another machine. And that machine has its own set of limits. So that logic is what you can apply to anything to do with energy. So then when you do that, you have to start with the first principle. Is that there's no such thing, and it's a principle that I'd say not non-facetiously, but it sounds like I'm being facetious. There's no such thing as renewable energy. It's a total misnomer because all energy is free. We didn't invent any energy. Wind, sun, moving water, oil, gas, coal, they exist. We didn't invent them. They're in nature. To convert the energy sources of nature into something useful for human beings, we have to do two things, and it's true for all energy machines. We have to have access to land where the particular source is abundant and therefore accessible, which you have to pay somebody for, always. For most of human history. And secondly, you have to build machines out of materials from the earth to tap the energy to make it useful for all things, right? Whether it's oil or wind. And since all machines wear out, there's no such thing as renewable energy. All machines wear out. The idea that the wind keeps blowing is, so what? We're not running out of oil either. It's not the point. That people thought we were at one time, but we're not. Whether you want to use it or not is then a machine decision, which is derivatively a money decision. And then derivatively, which people ignore, an environmental decision, because how much material you need to use is, to your earlier point, a density derivative. It's how dense is the energy form. If it's not dense, like wind is not, hydro's not, you need lots of machinery to collect the energy to get the same amount of energy. And the lots of machinery leads lots of mining. So that takes me into the two sort of limit spaces that I addressed in my two papers. One is the physics limit. You can't get more photons on Earth than are delivered to the surface of the Earth. So if you assumed 100% of those photons became electrons, you know the limit to what a solar panel is. That's the limit. First, you can't collect 100% ever, and you can never turn 100% into electrons. So you actually know what the limit is, and the limit is in the physics of the conversion of the photons to electrons. For silicon photovoltaic cells, it's called the Shockley limit. It's about 33%. And if you know that solar panels are the best commercial ones ship at 27% and change today, you're not far from the physics limits for solar panels, which are silicon ones, which are the dominant, in fact, the only really Earth-based economic source of solar power. So the 10x nomenclature, all this stuff's getting better at 10x. It did get better 10x in the last decade and a half. It did. When you were 2% efficient, you become 20% efficient, you're 10x better.
Yeah.
You can't go from 20% to 200% efficient. This is silly. I mean, it just, and that's, so the 10x this exponential 10x gains are silly. So now what you're in is a domain of how much better can it get in terms of manufacturing efficacy of the underlying materials. And then that takes you into the second domain. How many materials do you need to use? Where do you get them? How do you get them? And if you're already near the physics limits of efficiency, then the quantity of materials you need to dig out of the earth, tons of ore gigawatt hour of electricity doesn't change much. You get a little bit better. I mean, but again, you know the limits. You can't perfectly get ore out of the ground, and you can't perfectly convert it into a device, and you can't perfectly manufacture a device. So you can look at the ranges turn out they're rather narrow. I mean, there are no 10x ranges. We're really good at getting ore out of the ground. We've been doing it for, I don't know, 10,000 years. We've got a lot better at it. We're not at the limits of what we can do, getting copper and, you know, neodymium and cobalt and lithium out of the earth. We could do a lot better, not 10x better, and certainly not in any timeframes that are meaningful. So that's the predicate of how I think about it. And then you begin to ask questions like, well, let's use, if you take for every gigawatt hour of energy delivered into the citizenry, we know today, building the machines that exist today, that we have to mine and process roughly 10 times more materials using wind and solar and hydro than using gas, coal, and oil. 10 times more of the earth has to be dug up and processed per unit of energy delivered, for the same unit of energy delivered, just to build the machines. And then if we look at electric cars, which are they're the poster child of the transition, it's not hard to figure out. And again, you don't have to be a graduate student. High school students can do this research. Look up the size of the battery. It's about 1,000 pounds in an battery electric vehicle. How many pounds of those things are steel, copper, aluminum, cobalt, manganese? Go through the list. Lithium, obviously, because they're almost all lithium batteries. And then you just look up the ore grades for those materials. Where do they come from? How do we process them? And what you discover is, on average, one car, its 1,000-pound battery, requires mining and processing about 500,000 pounds of materials. It's a lot of stuff for one car. And it's being mined somewhere. Now, some of it's in Canada, because Canadians still like to mine.
Right.
Some of it's in Australia. Australians like to mine. Increasingly, a lot of it's in places like the Arctic, in Russia, in Africa, in China, especially for rare earths. I mean, the rare earths
does this follow a pattern of kind of offshoring, and you go to places where there's weak labor laws and environmental laws, or just that phenomenon of people not being able to see under the hood. It's literally because it's not in our backyards. We don't confront it every day. We don't see it, and so the product arrives, and it's just this magical experience of opening up your new iPhone box or whatever. But you don't see everything that's led up to that moment.
Well, so exactly right. You need to, I worked as a mechanic in school. I raced Grand Prix in Canada in a motorcycle, and I worked summers as a mechanic. So I like lifting up hoods like your son.
Right.
How does this work? And most people don't care what's under the hood of their car. They don't really care if it's an electric motor. I mean, most people, and we know that most people don't care because they aren't buying electric cars. Tesla buyers buy Teslas. But in North America, something like 90% of all electric car sales have been Teslas. Globally, it's almost half. So it's a phenomenon for Tesla, whether or not that's because people like Elon Musk and Teslas. It's not the best electric car. It's a great electric car. Others are as good. But when you lift up the hood and you see a simple electric motor, you say, well, it's much better than an internal combustion engine. It's simpler. It is. It's got two moving parts. And there's, give or take, maybe 1,000 moving, different parts in an internal combustion engine. But the batteries also we just inverted where the complexity is, and nobody lifts up the hood of the battery. It contains thousands of parts. It has cooling systems. It has electronics in it. It has 7,000 to 15,000 welds. It's got all these different metals and materials. It weighs roughly 4 times more than an internal combustion engine. Some of them weigh 5 to 8 times more than an internal combustion engine. It's made from all these complex minerals. It's far more expensive by a factor of 10 than an internal combustion engine, far heavier and more dependent. And when you use it, everybody knows, they know. You have emissions from the power plant, so you try to gain the power plants. That's the least of it, even though that's poorly understood. To your point, what we've done is we've exported mining and carbon dioxide emissions to the sources of the minerals. We've done that to such an extent that in many parts of the world, it's demonstrably the case that the total emissions over the life of a car can be greater using an electric car than driving an internal combustion engine. The only places where they're not greater, clearly, is if you are charging fully on hydro dams in Norway or Sweden,
or in Ontario.
Drive an EV.
Off of our can-dos and hydro.
I think you need to be in Manitoba or Newfoundland, where it's
like all hydro.
Pretty much all hydro, like Norway.
Right.
But the burden, Let me put it this way. Here's the other part. We actually don't know what the burden is because it's such an opaque, labyrinthine supply chain to get to those batteries. The range of what would be the carbon debt when an electric car shows up in your driveway, it shows up with a carbon debt from making the battery.
Right, right.
The range of that debt is from 2 tons of CO2 for that one car to 20 tons. It's a 10-fold range, depending on where it's made and the assumptions you make about that.
And people talk a lot about this with renewable infrastructure, you know, this idea that there's an energy return on energy invested, and this wind turbine pays for itself, or it pays its carbon debt. But I think you've kind of called this like categorical errors, right? Because the energy that's the embodied energy of the product you've created is fossil fuels, right? It's these enormous mining trucks and diggers, as my son calls them, to kind of load up all these minerals and process
diggers are great.
them. And what you get at the other end is you get, you know, low carbon electricity, but it's not something that you can use then to build your next wind turbine. So, you know, I really enjoy another Canadian brethren of ours, Václav Smil, and you know, he talks about, like, you know, I'm fairly far along the kind of climate concern spectrum, you know, and that's part of what drives me to being pro-nuclear. But and I think, you know, Bill Gates very much references Václav Smil, but this idea that we live in a fossil fueled civilization. I mean, our fundamental building blocks like steel, cement, fertilizer, we haven't found a way around that just yet. And again, as part of this magical thinking, it's, you know, I was just speaking with a guy about Mark Z. Jacobson's plan, and we were sort of deconstructing that on the last podcast. And it's just, I don't know, it's maybe like playing a video game for these guys, or Sim City, where you can just kind of move pieces around on a board without understanding how incredibly complex and difficult it is. And, you know, getting back to the misapplication of Moore's law, you know, because in computing, I think you say that there's been a billion-fold increase in energy efficiency. Is that correct?
Yeah. Well, depending you're starting, but yeah, the key in computing has always been, people thought it was to make the transistor smaller. Mm-hmm. In early days, nobody cared about the size of the transistor because you're mainframes. What do you care? Right. What you were trying to do is reduce the energy of each logic operation, because you get more computing speed and more computing power by speeding up the switch, and that can only be done by cutting the amount of energy you needed for each switch. So you got that by shrinking them.
Right. So that's how you got the motivation.
The motivation was, well, ENIAC was a 20 kilowatt beast with 17,000 vacuum tubes. Now you can do a billion, you know, ENIACs with about 10 watts instead of, you know, 20 kilowatts. Wow. But the Moore's law seduction, and you see it all the time. And by the way, I love Václav Smil. He's brilliant, great writer, quote him all the time. He and I share common roots. My family's from Manitoba, as it turns out, my parents. But he's more worried than I am about climate change. Yeah. But my research has nothing to do with how anxious one is about it or not. I think energy transitions are inevitable. We keep finding new ways to produce and use energy, but we keep using the old ones. There's no period in human history where we've stopped using an old form of energy. We still use a lot of wood. Right. We still use a lot of hydropower. We still use a lot of coal. In fact, China's building, as you probably know, more coal plants than already exist in the world right now. They're phenomenal build rate plan from China, both in their own country and South Asia. But the Moore's law seduction, which gets cited all the time, is, oh, look, you naysayers, you were the same people that said that cell phones would never replace landlines. That's right. Well, first of all, no one ever said that. I don't know where that trope comes from. People in communications like I was knew that cell phones could replace landlines. That was the goal. It wasn't never. Yes, of course you could. That's what everybody rushed to do. But the analogy is silly for a very simple reason. The efficiency with which you can perform a logic operation has nothing to do with the efficiency with which you can create energy. Computers use energy. That is a related area of physics to how you create energy and power. They scale differently. And so you can, if it were the case, to show how silly it is, if it were the case that one could scale, let's use, I don't know, solar arrays, because they're made out of silicon like computer chips. Yeah. If a solar technology could scale like silicon technology for computing, that would mean that we are on track to making a solar cell the size of a postage stamp that would power a skyscraper by itself without any ancillary support.
Right.
That'll never happen. I mean, it's not, oh yeah, we'll get there, or let's spend money. It's
that's the language. Yeah, that's the language that gets used. I'm interested in exploring the underlying kind of reasons for this. But when you see, and it's very hard to find critical thinkers on renewables. I mean, that's why I found you, because I was just desperately searching around and not seeing anything certainly coming from my side of the political spectrum, which tends to be fairly kind of left or centrist. But renewables are treated with such soft gloves in the media. I mean, not even gloves, they're really kind of pampered along in terms of language that's incredibly optimistic, open-ended. We're going to get there one day. We don't quite have intermittency sorted out yet, but the implication is, right, oh, we'll be there soon. And that's always kind of puzzled me a little bit, because in my read of this is, renewables don't really challenge the supremacy of fossil fuels. And I mean, you're saying, of course, energy transitions, we're still burning wood, for God's sakes. None of this is going to completely disappear. But renewables, they lock in a backup system, right? If you look at, I think Václav Smil's talked about Germany in this way. They had sort of 90 gigawatts of traditional power generation. They built 110 gigawatts of wind and solar. They're still keeping that 90 gigawatts around. So in a way, like, the fossil fuel industry is not threatened by renewables appearing on the scene. And to me, that has to factor into why they get treated with such kind of soft gloves in the media. And I'm interested in your perspective on that, particularly because I see a lot of fossil fuel funded attacks on nuclear. And nuclear really does, fossil fuels interests do stand to gain from a nuclear plant shutting down, for instance.
Of course.
Like, when Indian Point closes, we're burning a lot of gas, or when Pickering closes next to me, I mean, we're going to be burning, I forget the calculation, it was something like 6 million square meters or cubic meters up here, but a lot of gas. Like, what do you think plays into the media landscape and the ways in which renewables are treated in the discourse?
Well, I like to say that I was trained as a physicist, not a psychologist. Trying to, but obviously I have opinions of why the media, why people believe things they believe. I would say the cynical part of me would point out there's an awful lot of money involved, trillions of dollars. So people engage in a cognitive dissonance about their beliefs. They don't want to question their beliefs. And you could say that on the hydrocarbon side. I mean, the oil industry is the biggest commodity in the world, full stop. It's bigger than all the metals and materials combined. So it's a big industry. They have a lot at stake. I would take issue with something you said, by the way. I've been around this debate a long time. There's so little money spent by the, quote, fossil fuel industry fighting nuclear power or fighting renewables. In fact, I would actually challenge anyone who makes that claim. It's a common claim made. It's sort of a claim that falls into the same camp as renewable energy is going to take over the world. Mm-hmm. One needs to point to where the money is, other than trade associations, which have been emasculated and do essentially nothing. There was a time when people spent money in their own self-interest to promote their products, because their products are what they do. You understand oil, you promote oil. Mm-hmm. You generally don't promote anti-ethanol. You could. People have done that in the past. So, right. I mean, I just dispute that there's actually very significant amount of money being spent, as opposed to the budgets of the top environmental groups, the top 20 environmental groups. Collective budgets are about $2 to $3 billion a year. They build nothing. All they do is do PR and lobby. So there's billions of dollars a year being spent promoting this green vision. Mm-hmm. Essentially no money by comparison, a few millions in trade associations, but I don't know.
I think Schellenberger's kind of documented that in pretty good detail, but I mean, it doesn't take a lot of money to sort of kick nuclear wells down. I would argue.
Well, no, people are afraid of nuclear energy, and they still are. But I didn't answer your question. It doesn't matter to me whether people spend money to say something is good or bad. Mm-hmm. Like you, I'm interested in the facts, and if people don't know that an all-electric car world, if we get there. In fact, there's a University of Toronto study that was funded by the Wall Street Journal to talk about how Tesla's beat Toyotas in the carbon footprint, counting the batteries. If you read the studies, you find out that's kind of a finger on the scale. Sometimes they do, sometimes they don't. But no one really talks about the material burden in the environmental costs and the energy costs of that. No one talks about the fact that 60% of the cost of an electric battery is in the materials, which are commodities. We're going to increase the demand of those commodities from 200 to 2,000%. And in every time in human history, without exception, for any commodity. When you increase its demand, the price goes up, not down. There's no exception. So what makes these forecasters think, just a question I've got for them, no one's answered it. What makes them think if we increase the demand for the commodities, nickel, cobalt, copper, manganese, and lithium by 10 to 100 fold, that the price is going to collapse all of a sudden? These are already commodities. So at best, the price stays the same. More likely, the price goes up, which means the cost of the batteries goes up. The break-even point recedes into the distance. These are not criticisms of, I like electric cars. We should have more of them. We will have more of them. Mm-hmm. But they're not going to replace all the internal combustion engines in the world. And even if we got 300 million electric cars, most of your listeners probably know there's about 7 million today, give or take, in the world. If we get to like 300 million, which is the optimistic forecast for the next 15 years, that displaces less than 10% of the world's oil.
Wow.
I mean, you could figure this out arithmetically. We look at where's the oil used, how much is used by light duty vehicles. You don't get to a big number. It's not the existential threat to oil. Now, 10% is not nothing if you're an oil trader. I mean, you take 10% of the supply off the market, prices really go up. And if you oversupply the market 10%, prices collapse, right? Mm-hmm. But is it an existential threat to the existence of oil? Come on. So, and then we're going to make airplanes all electrical. Okay, maybe one day if there's a battery that matches the energy density of, aviation fuel. But, the best batteries in aviation fuel, which if you measure what the metric that matters is energy per weight, not the density in pound terms. They're apart from each other by 5,000%. I mean, you got a big gap to close here. You can make small airplanes fly on batteries for short distances.
Yeah,
sure. Big airplanes flying fast, long distances. No, it's going to be oil.
No, it was very interesting just on kind of abstract terms. You talk about we're moving from a kind of gas and liquid based fuel system to one that's solids. And you said that has big implications just on transport. I mean, you're saying, I think a pipeline is the most efficient way to move a ton of, I mean, hopefully it's a liquid or a gas, right? But there's big implications to just moving all of these minerals around the planet.
Sure. Absolutely. Yeah. So if you did this in tons, if you're a shipper, you measure everything in tons.
Right.
So we could convert the oil consumption of the world, and IEA does, into tons per year per day instead of barrels per day. And what we do know is that if you switch from a it's dominantly liquid and gas fueled energy system to a dominantly solid one, not coal, talking about wind turbines and solar arrays and batteries, you increase the tonnage by about tenfold, maybe more. And so the absolute quantity of materials moved to serve the same amount of energy goes up 10x. And to your point, they're solids. So some of them are moving ships. That's fine. Ships are efficient for moving liquids and solids, but the rest are going to be moved not just on trains. Trains move, but in trucks. A lot of trucks get used. And then we'll have the circular, we'll make the trucks electric. Now we're into like this sort of silly Sisyphean loop, but we're going to have some kind of magical closed loop that the trucks will be electric. There are electric trucks. There's electric diggers too, but they really are lousy, frankly. It's great PR for the companies, but they're pretty lousy. The mining industry, by the way, is a factoid here. We're going to push the biggest increase in mining with green plans that the world has ever seen in all of humanity's history. And today, the mining industry uses more oil than global aviation used before the great lockdowns.
Yeah. And I think there's a growing sort of unease amongst elements of the environmental movement that are starting to process these facts. And, you see that in these neo-Malthusian films like Michael Moore's Planet of the Humans.
Yeah, sure. Yeah.
I think there's a new one called Bright Green Lies as well. Yeah. Of course, their answer is just that, we need to become cavemen, or I don't know, I guess we have to knock up every other human or something and drastically reduce the population, not them first, for sure. Right. But, there are other alternatives in terms of an energy transition. I had the pleasure of having Dr. Scott Tinker on the show a little while ago, and he was, I think, similarly kind of framing this. He was saying, like, we have to think about the environment in terms of these 4 pillars. Certainly atmosphere is one of those pillars, but land and the local air and the water. Yeah. And my sort of counter proposal was, nuclear does seem to answer a lot of those questions. And I think, in terms of the march up the energy density ladder, and in terms of contributing no air pollution, not impacting the atmosphere with CO2. And also, I mean, it's a solid, but it's tiny because
Yeah,
the
the
density,
volumes are
right?
trivial. They're
Yeah.
basically you're using all the material use in nukes is essentially and the steel and concrete to build the facility.
Right.
The fuel itself is, from a volume perspective, including the waste, is totally irrelevant. Now, look, there's no phenomenology that humans have ever discovered that is as profound as nuclear fission that's actually usable today. Fusion is sort of a cousin to fission in a way, and it's always 50 years in the future. It's still 50 years in the future, frankly, if that. Moving from muscle and human and labor, which was slave muscle and animal muscle, and the movement of wind and water, which was most of humanity, to fire, to combustion, was the ignition that brought the world the wealth and the prosperity it's had. That's what hydrocarbon combustion did. Going to nuclear fission is as big a leap, but it's technologically harder. So far, the problem we have with nukes is not that we shouldn't have more of them. We should. And we've gotten much better at figuring out how to design new kinds of reactors, is that nuclear power produces electricity. And until it produces electricity that is so profoundly cheap that you can use electricity to synthesize liquid fuels,
right,
you're going to keep using oil and gas for a lot of other things. So the vision is, well, we can synthesize hydrogen, right?
Right.
That's true. I mean, we can do this. It's vastly more expensive than using natural gas, which is mostly hydrogen anyways. I mean, the CH4 is the C is one. There's four H's for one C. So you got a lot of hydrogen there. You can strip the carbon out if you want, or you can burn the carbon. I mean, and capture it. All those things are far cheaper than hydrogen. Hydrogen is a devilishly hard fuel to make at any price and transport. It embrittles metals. There's this huge fashion now to chase hydrogen. And the reason that fashion is there is for exactly what you're pointing out. If once you go down the path of saying we want to electrify things, you then figure out there's a lot of stuff you can't electrify. So what do you use if you're not using oil and gas? Well, magic, we're going to use hydrogen. Okay, more magical thinking about where the chemistry lies, where the physics lie, where the costs lie. We will do different things in the future than the past, but the society level ways of providing food and fuel, which are essential to civilization, food and fuel are, of course, exactly the same thing. Food is human fuel, and it's made with non-human fuel, and we got lots of it because of hydrocarbons produced. There's no reason for anybody in the world to starve except for politics. We can produce all the food the world needs trivially now, and will ever need. This is it's the first time in human history that's not been a problem, except for the politicians, the corrupt ones around the world who starve their people, and bad political systems that starve people. But the rest of civilization needs fuel too. Everything needs fuel. We're talking on Zoom, and I've done these calculations, which make the Greens unhappy, I know. But roughly 1 hour of Zoom on average is like your personal energy allocation. Each of ours right now is about the same as going 5 miles on a bus. And if I make the Zoom better with lower latency and maybe get it into holography later, then it's going to be like 20 miles on a bus, because even though the energy efficiency of pixels will get better, the pixel density to go to holography and 3D is just off the charts, right? Which has been the story of the internet from day one. Far more efficient with every year that goes by, but the efficiency gains have been more than offset by these astronomical gains in bit traffic.
Right.
But we're going to need lots more energy for lots of stuff: for cars, for Zooming, for medicines. Pharmaceutical industry. Speaking of that's
relevant right now. Yeah.
A little bit relevant. It's one of the most energy intensive industries on the planet. It's right up there with manufacturing semiconductors, producing and inventing vaccines and transporting them. We use supercomputers now to model bacteria. Running a simulation in a supercomputer, just one, and we have to do. We want to do millions of simulations ultimately. But right now, using a supercomputer to run simulations once, it's about equal to 10,000 cars worth of fuel per year with one simulation that runs for half a day.
Wow.
Data centers already consume this more electricity in the country of Japan. So they consumed zero 25 years ago.
I was talking to the head of the World Nuclear Association China director, and I guess my hope and aspiration would be that China could embark on something like a French Mesmer plan and nuclearize at least their electricity sector and
good luck.
deal with some missions that way. No, and what he said is, listen, the development and the deployment of 5G in China is going to use as much electricity as is being currently produced by the entire reactor fleet.
Well, he's right, and most people. Yeah. When you study the physics of information transport, which is utterly fascinating, it's my other hobby, so to speak. My book, Digital Cathedrals, is on that subject. So 5G is magical because it offers essentially fiber speed wirelessly, right? So you get rid of latency, you allow the kinds of things that we'd like to do to really get high resolution images or transport of these phenomenal amounts of data effectively. But it's roughly 10 times more energy intensive per unit of information, or per square foot of coverage than what it replaces. That's been the trend for a long time. In fact, roughly a quarter of all the energy consumed by the cloud, when we think of the cloud as making computers, putting computers in your pockets, having networks, it's the network. The network may become a third of the energy rather than the data centers, but both are growing. It's the only time the word exponential applies, by the way. The overused word exponential is very few things that exist keep growing at an exponential rate. The one thing that does is consumption of data. But
everybody likes the Fibonacci sequence. But yeah, the exponential is a rare phenomenon. Yeah,
very rare. Well, it's actually exponential early.
Right,
and then,
right.
Then the exponent ends because back to our physics limits, the bacteria cultures don't keep growing at exponential rates. They self-limit, society self-limits, but look, the thing that's, I would think, frustrating is there's a basic premise. It's frustrating to me, it may be to you too. Politics don't matter about a couple of basic premises. Everyone prefers to live on a planet where we minimize our destruction of each square foot of the surface, the precious layer that we live on. Everyone wants their air and water clean. I mean, this is there's nobody doesn't like that or want that. And it's been the consequence of wealth and technology that we can have so many people living so well with so little damage to our environment. Right? And to get progress where we have even less damage to our environment in all its forms, the air, the land we use, and the water, we then have to increase our energy densities, increase the use of technology to get greater wealth. Those are the things that are key, things that we do to take us backwards, that rob the economy of wealth, rob the ability for society to preserve the environment. Poorer societies, we know, you know this, don't have the money, the luxury of the kind of allocation of wealth we have to a clean environment.
Build sewage systems, and
they don't have the money. They just don't. So how do we get them the money? What are we going to do? So what we're proposing to do, and this is, economists, I'm not an economist, I don't even play one on TV, but economists would call this productivity. You want more output for fewer inputs, both labor and materials.
Yeah.
Okay, let's talk about the experiment we're about to undertake. We're about to switch over our energy production system, particularly electricity, to one that uses more inputs, more land, more dollars, more materials to produce the same output. This is backwards. And yes, it will create jobs. So we're giving everybody a shovel and 40 acres and a mule. This is the polar opposite of how you create wealth. We're actually going backwards, and it's an epic mistake because it will ultimately take wealth out of society to get not more of something, but less of something. That's environmentally destructive. That, to me, is frankly morally offensive. It's a very bad idea.
Well, what blows my mind as well is that, in terms of wind and solar infrastructure in particular, and probably some natural gas things now, none of the stuff we build today will be operating by 2050. By, some of these metrics end at 2050. And I was looking at Jacobson's plan the other day, and it calls for, I think, 18 billion square meters of solar panels by 2050. And because you're building these sequentially over the years, by 2050, you need to be swapping out 1.23 million square meters per day forever of these solar panels.
Yeah, sure.
Which is the entire output of China's current solar industry.
Okay,
so
good.
That brings us to the kind of back door, the back end of this. We've kind of got under the hood. I guess we're getting into the muffler and the exhaust here of this magical thinking. Tell me a bit about the kind of recycling implications of disposing of these solar panels and wind turbines, what that looks like in terms of its impacts?
Well, we have two things that, as you know, a lot of environmentalists have figured out that the quantity of waste will be large and epic. Yeah. So we are told that we'll create a, quote, circular economy with some kind of perfect recycling. I mean, you know, this is a nice theory to spin. You just have to look across. We now are into about 40 years of global work and the wealthy economies at recycling. We have lots of data on how this works and doesn't work. And for some things, it works very well. For most things, it doesn't. And to be simplistic, let me explain why it doesn't. If I need more neodymium to make offshore wind turbines magnets, which is we use for a very specific reason, it's called a rare earth material, not because it's rare, it's because it has rare properties.
Oh, okay.
And we rarely mine it in America, but it's mined mostly in China. Yeah. And we mine it in Canada too. But the physical concentration as a percentage of tonnage of neodymium in waste wind turbines is lower than the physical concentration of neodymium in the ore, the native ore. Now, if you want to go mining for a mineral, the advantage of going to the native ore is not only is the concentration of it higher, but it's in homogeneous material and easier to get out.
Right.
The heterogeneous materials, which are trash, are much harder to handle, which is why recycling is hard and why it's therefore expensive and why it's actually environmentally destructive by itself. Our e-waste recycling, we ship offshore because it's expensive and dirty and dangerous. And China stopped, as you know, a couple of years ago, China closed its doors to that, which sort of ended the recycling of e-waste largely, except to countries like Indonesia, which just ignore the environmental costs and have, you know, kids doing things that are dangerous to try to recycle e-waste. So the recycling trope fails on every metric possible that's practical in any timeframes of any meaning to solve, quote, the problem.
Right.
The related problem, however, is one you put your foot on, is that even if you recycled everything that was coming offline, the amount of stuff that needs to be built for the next 50 years still requires virgin material. In fact, there's not anywhere close to enough recycled stuff to build all the new things that are imagined. So you're going to be mining net new material, even with perfect recycling, for a very, very long time. Then we add to that, this is UN data. The UN is not, the UN Environmental Program are not happy about the fact that wind turbine blades are not recyclable plastic. We were worried about plastic straws, supposedly, which are recyclable. One small wind farm, one tiny wind farm in Ontario has more non-recyclable plastic than all the world's plastic straws combined. And we're talking about increasing the volume of that plastic by 10,000-fold. Solar panels have a glass sheet on top of them, not a solar sheet, but a glass sheet that's infused with metals to get the glass stability and transparency. Right? Mm. Those metals make the glass panels, forget the rest of actually hazardous waste, which means they have to be disposed of as hazardous waste. So the whole solar industry, by the year 2030, 2040, depending on whose forecasts, will generate more volume of waste in the global plastics industry. But the difference will be they'll be generating a volume of plastic hazardous, glass hazardous waste that's greater than and more hazardous than plastics, much more difficult to recycle, basically trash. Not impossible to recycle, just environmentally challenging and expensive. These chimerical plans to do these things are, they're exercises in Excel spreadsheets. They have no basis in living in the planet that we have to live on.
Mm-hmm. So I think one of the key questions here is in terms of communicating this is this idea of scale. And I've talked about this a few times, just numeracy is really tough. And before I started looking into energy, a difference between a megawatt, a gigawatt, a terawatt, a petawatt, these things were really abstract concepts. So maybe just as we're kind of closing, how do you, I found that reading your work, I do find a way where I can sort of conceptualize and visualize the big numbers that you're talking about. But do you have any sort of pointers or tips in terms of communicating the scale issue?
I tell, when I do lectures with students, I tell them they can do, this is elementary school arithmetic. So the scale doesn't require knowledge of algebra or calculus. It's just arithmetic. Right. And you can look up the facts. How many cars are there? How big are the batteries? How much cobalt? Then you find out that the current fleet of electric cars in North America, which is very small, right? We're talking Canada, United States combined about 1 million cars. That's 1 billion cell phones worth of cobalt alone. 1 billion, and that's just 1 million cars, and there's 1 billion cars in the world. So
Right.
now we can do arithmetic here. 1 billion times 1 billion is a big number. It's more than 1 trillion.
Yeah.
And I mean, you get these incredible quantities of materials. So the innumeracy is epic. The magical thinking is epic. They all will be more efficient. Well, yes, okay. Let's be more efficient. Obviously, who opposes efficiency? But efficiency always has a cost. So efficiency is meaningful in business, is if it reduces the cost of the final product. So you can deliver it cheaper to somebody and still stay in business. If the efficiency costs me money, it's not efficiency by definition. It may be a material efficiency, but it's not really economic efficiency. I don't know what the solution is. I think because there's so much emotional, quasi-religious attachment to the idea that we have to do something about carbon dioxide. And if you believe that, for example, then I would say, well, the cheaper have to do something would be to improve the efficiency of existing internal combustion engines. There's a lot more headroom in that because Carnot's limit, thermodynamics limit's much further away than the battery's limit for efficiency improvements. Be much cheaper, have a lot greater efficiency gains, a lot greater reductions in fuel use, which is sort of what's happening. If you really want to spend taxpayers' money to accelerate it, instead of subsidizing Teslas, you'd subsidize the equivalent in an internal combustion engine.
Yeah, I mean, Václav talks about this, and he laments the fact that our engines have gotten so much more efficient, but we've decided that rather than using a 1-ton car, that we need a 2 or 3 ton SUV, and so we've eliminated all of those efficiencies.
So Václav, to be kind to him, because he and I have argued about this, is what he really wants is everybody to live the way they lived
in the 60s, right?
A century ago or 80 years ago, in terms of their what they did, how often they traveled, how big their house was, how safe their car was, how comfortable it was. So with the efficiencies we have today, living in a 1-bathroom, 3-bedroom, 1,000-square-foot ranch, driving only 1 car that weighed only 1,500 pounds and taking 1 airplane trip a year for a vacation and never straying more than 50 miles from your home, which a lot of humanity still does in the poor parts of the world, we could cut global energy use. Human nature likes comfort, convenience, speed, safety. Those 4 features of existence always cost energy. Yeah. Always. And people always want more of that. And I didn't add entertainment. The entertainment industry is a $2 trillion global industry. And Netflix is virtue signaling how they're going to cut their carbon footprint by having batteries instead of diesel generators when they film movies. Oh, isn't that cute? Yeah. It's such silly virtue signaling. But when just the delivery of the product itself consumes far more energy than creating that product.
I've got one last question for you. I know we're a little constrained on time, but from my understanding, with fracking, we're hitting the source rock. And there is the potential, we've talked about peak oil and the fracking revolution obviously set that off some distance, but we will eventually, I think, get to those kind of limits. Do you think that fission is the natural sort of transition that we will end up with? I mean, certainly if we didn't have plentiful fossil fuels, I think the entertaining of the renewables fantasy would be much less prevalent because you just wouldn't have the firming, or the firming resources would be so much more expensive. Or maybe there would be a rationale because you're sparing fossil fuels by using some renewables. But do you think there's inevitability of that transition up the density ladder there?
Well, sure. First, in time frames that are meaningful, by that I mean we're talking centuries.
Yeah.
There's no limit to hydrocarbons in the time frames that are meaningful.
Really? Okay.
So if we're talking about the geophysical nature of the planet Earth, okay, sure, there's limits to everything. But in time frames that matter, 2, 3, 4, 5 centuries, there's no limits to hydrocarbons. But that has nothing to do with my conviction, like yours, that we will, of course, march up the ladder of energy density. We won't forever march. We're going backwards there's be lots of windmills and solar arrays. There's lots of uses for them as a complement to the need for electricity on grids in different parts of the world. They make no sense in northern latitudes. Give me a break. Yeah. As Václav has pointed out, the actual operating delivery of electricity from solar panels in Germany and in Northern Ontario is about 5% of the rated capacity. Yeah. So what that really means when they tell you it's grid parity, you multiply the number by 20 to get the actual cost if you were going to depending on that for all your electricity.
Right.
By at least 20. So do we do more nukes eventually? Absolutely. I mean, there's nothing close as the only thing that's in fact magical. We all studied You can't create or destroy matter and energy except in a nuclear reactor. You actually create energy by destroying matter. It's quasi-theological. It's amazing. It's just really, really hard to make machines to do it inexpensively. We're very close to doing that. I mean, the new machines some of them are Canadian, some are US. There's a couple of European ones. Boy, really very impressive machines. A plug and play super safe reactor that just is 50 to 100 feet underground in a village somewhere that just runs for 20 years between refuelings and has an on-off switch. That's it. Now that can't cycle anything. You're still going to be doing something to go peaks and valleys.
Yeah.
It won't be batteries until physicists figure out how to make cheap superconductors. That could happen one day. If I were looking at research money, what's the magic for the future? You want a perfect future where we don't emit anything? Cheap nukes and cheap superconductors. Then you assuming, by the way, you can make them using electricity.
right.
Burning hydrocarbons, which let's stipulate you probably could. Then you have this perfect physics combination that is unlimited because of the phenomenology is profound. I have no doubt those things are possible. I'm also equally confident that they won't happen in the next decade or two.
Yeah.
We're going to be working on inventing those things in the next decade or two. I'm extremely optimistic about those inventions becoming real somewhere, somehow, but they won't become real because someone says, I need it now. Mm-hmm. That's not how physics and science work. It's too bad. I wish it did.
Yeah. You got to spend the money in the basic research. Yeah.
Yeah.
Mark, thank you so much for coming on. It's been a pleasure chatting with you. And for my listeners, where can they find more of your appearances or your work? You've written a number of books, I understand. Just give our listeners a sense of where they can find you on the internet and where they can buy your books.
Well, yeah. Well, the magic Google machine with my middle initial, Mark P. Mills, gets you to both the Manhattan Institute website and then my Tech Pundit website. I have a new book coming out this October, which has some sections on energy, but it's really about technology. You're the first one. I'll preview the title too. It's called The Roaring 20s, The Roaring 2020s.
Wow.
I'm very, very, very optimistic about this coming decade.
Yeah. Well, you heard it breaking here on Decouple. Okay. Mark, thanks again for making the time.
Thanks for having me on. Take care.
All the best. If you enjoyed the podcast, please make sure to subscribe, like, and review us on your podcast platform of choice. Until next time, guys.